Okay, so we are going to do the exponential equations now. And again, we start out by drawing our little template. So remember that domain is left to right. That's our x. And range is bottom to top. That's our y. So looking at the first example, with exponentials, you'll notice that if you go left to right, the first thing we see is a left arrow, and the last thing we see is an arrow. So for the most part, the domain will also be all real numbers, just like the quadratics. There are some exceptions, but that's pretty much the normal. What's different is the range. And when I highlighted the x-axis, I was also highlighting the fact that this graph looks like it's coming closer and closer to the x-axis, but it's actually never going to reach it, because you cannot get a y equals 1 with any exponential if it's the normal setup. So you can do put in the tiniest x you want, and you'll still never reach 0. You'll still never reach y equals 0. So that tells us what our range is. It's not actually what it's starting out and stopping at. It's what it is. It's what it's starting from, but it's really not starting there. It's just approaching it. So it's starting at 0. So it starts here. You can imagine it having an actual open hole every time at 0 and going to infinity. So we call that place where it's approaching something called an asymptote. So it's actually a place where the quadratic equation approaches but never touches. So at y equals 0, there's like a wall there stopping the graph from continuing to come down. Okay, so on this one, again, we have arrow to arrow for all real numbers on our domain. And this time we want to see, well, what is it coming up towards? So if you look at the graph, it looks like it's climbing, and right here it starts to flatten out. Where that flattening out is, that's your asymptote. I need to clear that. That's our asymptote. So we draw a dotted line right there and say that is y is 0. That's my asymptote. So that's where the start or stop is. Now we have to look at the graph. Well, we are coming from a hole, the asymptote, and it's coming from an arrow at the bottom, because we're starting from the bottom and going up, and we're hitting a wall at that y equals 0. And that is where our hole would be. So our range here is y is less than but not equal to 0, because there's a wall stopping you. Okay, next one we had to use, I used a calculator to draw it, but again, you could plot your dots on the graph. So at -1, we're at 1.5, at 0, we're at 1, at 1, we're at 2, at 2, we're at 4, and at 3, we're at 8. So it kind of does this number, which you do see on my calculator graph, and I will show you how to do that. Again, this is representing a function, so that means all real numbers. It didn't say that that this was the only points. It does say function. That tells us it keeps going. And then now we need to figure out where is it starting from. Well, it looks like it's approaching but not getting to 0 again, and this time it's going up. So our y is greater than 0, because our asymptote is at y equals 0. All right, our next example gave us just an equation, so I used the TI Inspire to graph the picture. Because it is an exponential, we know that the domain is all real numbers. If you're looking at your calculator, if the graph goes off the screen, it is arrow to arrow. So for range, we need to see, where does it look like this graph seems to be falling to and touching but not falling below? And that's going to give us our clue to where our asymptote is. So our asymptote in this case is at y is 0. And again, for exponential asymptotes tell us where the number that we're looking for, the whole for our range, and then we have to decide is it above or below. In this case, it's a range whole at the bottom, asymptote at the bottom, and then it is going to an arrow. So we have it is greater than but not equal to. Exponential range should never have an equal to sign. Kind of a clue. Okay, last pieces is our exponential explanation. It's always going to reference the y-intercept because it's the one thing that is true about all exponentials, that they go through the y-intercept at a specific spot. But this time it has been moved up to 2, which means we need to, our graph has been shifted up by 1. Because normally, if you look at this one up here, it's, well, that's not the best one. I know. Let's look at the, see, it crosses at 1. That's the normal spot where it crosses. So it's been shifted up at 1, which means our asymptote has also been shifted up by 1. So our asymptote is now at y is 1. And the rest of the graph, we can just guesstimate that it kind of does this number. Okay? So where the y-intercept goes, if it goes up by 2, then the asymptote moves up by 1 because it's always 1 less, because it always crosses, normally it crosses at the 1.1. So we have all real numbers again because it did say it's an exponential. Also, growth means that it's climbing up. And now we have our range as y is greater than, not 0, 1, because our asymptote has been moved up by 1. And it's a growth, so it looks like it's climbing up. The next one says decay. Decay means that it's falling down. So we have to take and find where's our point at. It's at 4, which means it's been moved up 1, 2, 3. So our asymptote is now right here. And the exponential decay means that the graph looks like it's falling down. So it's starting at the top and coming this way. That doesn't really affect our domain or range, but it does affect what the graph looks like. So again, all real numbers for our domain. And this time we have x is greater than 4. Y is greater than 4. So it's falling down. Okay, that's it.